Okay, so the next part is this entropy. We will understand this term now. What is its significance? What are its calculations? Okay. So entropy is nothing but if you talk about the physical significance, then it is a measure of the randomness or chaos. If a system is chaotic or if there is disorder, then I can say that its entropy is high. For example, if a person is running, then his entropy is high. But if a person is sitting at one place, his entropy is low. Why? Because if a person is sitting at one place, he is not in motion. That means his disturbance or the chaos in his body is less. He is not moving much. He is just sitting at one particular place. So this is just one example to make you understand. Similarly, if I say I'm talking, then definitely my entropy is high. But if I'm silent, absolutely silent, then my entropy is low. So more the disorder, more is the entropy. If I say I'm mixing two components, if I say that I'm mixing two components, then again I can say that because I have mixed two components, the entropy will increase after the mixture is formed. Why? Because initially, before the mixture had been formed, we had separate two components, individually two distinct components we had, and they both were individually separated from each other. Each had its own system of rest. But when you are mixing the two components, because of the mixing, there will be disorder, right? The particles will move from one place to another. And after that, you can say that because of this mixing, definitely the disorder has increased from what it was when they were separate. So entropy is a measure of the disorder or a chaos in a system. This is the significance in order to understand the concept. We will get into the mathematical portion of it. Entropy is an extensive property. That is, it depends on the number of moles present. It depends on the quantity of matter present. So more the quantity of matter, more will be the entropy. So if I have more amount of gas, then the entropy will be more. If I have less amount of a gas, the entropy will be less. Entropy is a state function, so it will just depend. That means the change in entropy will just depend on the initial and final states of the system. I don't have to take into account what has the path been because it's a state function. So it will just depend on the initial and final states of the system. Now, change in entropy is denoted by delta S. Delta is change. So I can say that delta S is nothing but S2 minus S1. So what is S2? S2 is the final entropy. S1 is the initial entropy. So after a process is over, if I want to measure the change in entropy, I'll say that delta S is denoted by S2 minus S1. So that delta S is nothing but the change in entropy. Anything which has a delta means final value minus initial value. So delta S is equal to S2 minus S1. Capital S is entropy. Final value of entropy is S2. Initial value of entropy is S1. SI unit of delta S is joule per Kelvin. So this is the SI unit. Joule is the unit of energy and Kelvin is the unit of temperature. So the SI unit of delta S is joule per Kelvin. Joule per Kelvin. How do you write that? You can write it in this way also. That is joule. Capital J is joule and per Kelvin. So joule per Kelvin. Okay. Now calculations and other parts of the definition. So first we'll understand the two concepts, that is system and surroundings, the change in entropy of system, the change in entropy of surroundings. And then we will get into the calculations concerning those parameters. Now, delta S system. What is my system? Whatever I'm considering for understanding is called system. Whatever I'm studying is called system. Whatever is outside the system is the surroundings. So if I say delta S system plus delta S surroundings, that means I'm basically calculating the total value of change in entropy. That is a combined value of change in entropy. The combined value of change in entropy is nothing but delta S total. Total, because you have added the two delta S values. So you call it delta S total. So what is delta S total? Delta S total is nothing but the sum of entropy change in system and entropy change in surroundings. So the sum of delta S of system and delta S of surroundings is called delta S total. Total delta S. Also, you should know that this total delta S is called delta S of universe, because you know that system plus surroundings is equal to universe. So everything is a part of the universe. So if I want to measure delta S universe, it's nothing but it's equal to delta S total. That means I have to calculate delta S system. I have to calculate delta S of surroundings. I'll add up the two and then I'll say that this is the total value of delta S universe. So delta S total is also denoted by delta S universe. So in some books they write delta S total, in some books they write delta S universe. So what is universe? Universe is system plus surroundings. Mathematically, now let's get into the mathematical definition. Okay. So mathematically, delta S, delta S is defined as integral of dq upon t. dq is heat exchanged. It could be heat gained, it could be heat lost, anything, but it is heat exchanged upon temperature at which the heat is exchanged, or the temperature, if the temperature is differing, that is, if the temperature is changing during the process, then definitely we have to integrate it. So the temperature will remain inside the integral. It cannot be taken outside the integral if the temperature is not constant. Because in mathematics, if a value is constant, then I can take that value outside the integral sign. But if a value is not constant in mathematics, we cannot take that value outside the integral sign. We have to integrate the entire expression. So whatever is not constant has to be integrated properly. Whatever is constant can be taken outside the integral sign. Now, delta S system is equal to integral of dq system upon t system. SYS is the short form of system. And delta surroundings is integral of dq surroundings upon t surroundings. SURR is the short form of surroundings. So SYS is system and SURR is surroundings. That is the notation I have used. So let's understand these terms now. As I said, temperature of system may be a constant during a process or it may change. So if it's isothermal, then definitely temperature is constant. But if it is not isothermal, then temperature is not constant. So accordingly, we have to integrate. If temperature is constant, that constant temperature can be taken outside the integral. If temperature is not constant, then it has to be taken, it cannot be taken outside the integral. It will be present inside and it has to be integrated. So some knowledge of integration is required. Okay. Now, what is dq system? dq system is always the dq value that would be obtained in a reversible process. This is by definition. Means what? If I have a process wherein the initial state of the system is A and the final state of the system is B. Let's say I have initial state as A and final state as B. Right? This is the initial state. A system is going from A to B. So it may go from A to B, let's say via a reversible process. So if I say that the state of the system is changing from A to B by a reversible process, that means I'm carrying out a reversible process, and because of that the system has undergone a change in its state. So the initial state of the system was A and the final state of the system is B. Fine. Now what is then dq? This dq of system, if I'm talking about dq of system, then I have to look at the reversible path only, which means that whatever reversible path is possible between A and B has to be chosen for calculating the value of dq of system. I repeat, whatever may be the process, maybe the process is reversible, the process may be irreversible. I'm talking about the actual process. Let's say I'm carrying out a process wherein the system is undergoing a change in its state from A to B. Now that process may be anything. That process may be irreversible, that process may be reversible, that process may be isopodic, that process may be isobaric, that process may be isothermal. It could be any type of process that I'm carrying out. But when I'm calculating the value of dq system, then as per the definition or as per the rule or convention, strictly I must take into account only and only a reversible process that could exist between state A and state B. So even if the process actually is irreversible, I still have to consider an alternative reversible path between A and B in order to calculate the value of dq reversible. That means what? Irrespective of whether the actual process is reversible or not, but I have to always choose a reversible path between A and B in order to calculate the value of dq system. This is the convention followed for dq system. So what is dq system? dq system is that value of heat is changed by the system when the system undergoes a reversible process to reach state B from state A. Right? So dq system is that value of heat exchanged. That value of heat exchanged by the system when the system undergoes a change in its state from A to B by a reversible process or maybe by a series of reversible processes. That value of dq system is always taken for calculation, which is possible only and only when there is a reversible path between state A and state B. So this is what you have to keep in mind. So I have mentioned that here. dq system refers to the heat gained or lost by a system if the same final state, what is the final state? That means B. B is my final state and A is my initial state. So if this is my final state, then the same final state, that is B, is achieved or reached by subjecting the system to a reversible process or a series of reversible processes. So if I'm subjecting the system to a reversible process or a series of reversible processes, and then I reach point B or state B, those reversible paths are supposed to be taken into consideration for calculating the value of dq system. So whenever I'm calculating dq system in this formula, I always need to take into account a reversible process between state A and state B. That is the mathematical definition of delta Q or dq of system. But for delta S surroundings, no such thing is followed. For delta S of surroundings, we will take into account the actual heat gained or lost by the surroundings. That time we need not talk about an imaginary or alternative reversible path. We have to take into account the actual heat gained or lost by the surroundings in the actual process that has actually taken place in reality. So for DQ surroundings, that is the heat gained or lost by the surroundings, you need not consider, or you don't have to consider any reversible process. You directly consider the heat gained or lost by the surroundings. So whatever is the actual value of heat gained or lost, that is nothing but DQ surroundings. So whatever actual value of heat gained or lost is done by the surroundings is taken for calculating the DQ surroundings. But for system, we cannot directly take the value of DQ. We cannot take the actual value of DQ. Why? Because we first need to imagine or devise an alternative reversible path between path state A and state B. And then for that reversible path existing between state A and state B, we calculate the value of heat gained or lost. So DQ system is strictly the reversible heat gained or lost by the system. Whereas DQ surroundings is not necessarily the reversible heat, it is the actual heat that has taken place in the actual process or the actual path. That means it could be reversible, it could be irreversible, depending on the actual path. When we do calculations, then this will become clearer. So we will gradually go in this. So next point, if I'm talking about molar entropy will have the unit as joule per mole Kelvin because I'm restricting my definition to 1 mole of the component. So molar entropy will be what? The entropy of 1 mole of the system or 1 mole of the surroundings, whatever. But the unit is joule per mole Kelvin. Similarly, if I'm saying delta S molar, that is change in molar entropy. Delta S molar or molar delta S, that is change in molar entropy, will also have the unit of joule per mole Kelvin. So what is change in molar entropy? Change in entropy of 1 mole of the system is called change in molar entropy. So change in entropy of 1 mole of the system is nothing but the change in molar entropy of the system. Molar word indicates that I am restricting my discussion to 1 mole of the system or 1 mole of the surroundings. So joule per mole Kelvin will be the unit of delta S molar or change in molar entropy. If entropy increases, then delta S is positive, and if entropy decreases, then delta S is negative. Obviously, as I said, if I'm keeping some objects on a table, let's say the objects are placed nicely on a table. After some time, I throw all those objects on the floor. I just start throwing the objects on the floor. So if I just throw them to the ground, I can say that the entropy has increased because initially they all were placed on the table. Now, randomly, without any position, without assigning any position on the floor or on the ground, I just have thrown those components. So the objects have been thrown randomly on the floor without thinking as to where they should be placed on the floor. That means the entropy has increased. Why? Because the disorder has increased. Now, initially, when you had not thrown the objects were nicely placed on a table. So that time their entropy was low. But once you have thrown the objects, the entropy has increased because now it is a chaotic situation. So I can say delta S is positive because entropy has increased. If entropy decreases, that means delta S is negative. Let's say there are many things which are kept. There are many things which are just lying on the ground. I pick one by one from the floor. I start picking the components or objects from the floor. I pick them one by one, and then I keep all of them properly arranged, maybe on a table. I keep them properly on a table. How do I keep them? Maybe I arrange them based on the color. Maybe I say that all red components will be kept in this row, in the first row. All blue components will be kept in the second row. And in this way, I arrange all the components on a large table. So what have I done? I have basically reduced the chaos or randomness. So I can say that delta S would be negative in this situation. So calculations related to delta S. So in chemistry, whatever calculations that we need to do will be discussed. So whatever calculations we need to do in chemistry will be discussed one by one. Now, before that, briefly, I'll take you back. I'll take you back to the concept of reversible process, reversible and irreversible processes. So let's come to that. Now, if we go back to reversible and irreversible process, then things will be clearer. So I'll take you back to the reversible process once more, so that you can understand delta S of reversible process and irreversible process. Let's say that I have a reversible expansion of a gas, or I have an isothermal reversible expansion of a gas. I'm talking about an isothermal expansion now. So let's understand this process. I have a cylinder or beaker type of thing fitted with a piston, and this piston has some components or some weights kept on the surface. Okay? There are some weights kept. These are what? These are weights. Small weights, maybe very tiny particles, or let's say we are keeping sand particles. It will be more easy for you to imagine or to visualize. Let's say we have kept many sand particles. There are many sand particles which have been kept. Now, here we have gas. Here what do we have? Here we have gas. Right. Here we have gas. And let's say this piston is movable. Okay, so this is a movable piston. Movable piston, and this is a gas. So this is my system. What is my system? My system is gas particles, or the entire gas which is present inside the cylinder. That is my system. The gas present inside the cylinder is my system. Also, I say that this wall is conducting or diathermal. Means what? Means it can absorb heat or release heat. So it can take heat from the surroundings, or it can give heat to the surroundings, depending on the process. But definitely this is conducting. Then only heat can pass through this. So this is a conducting or a diathermal wall or a surface. Now let's come to the reversible expansion. See, the surroundings are much larger than the system, because everything is a part of surroundings. Whatever is not a part of this cylinder is a part of surroundings. That means whatever is lying outside the cylinder is a part of my surroundings. So this also has to be clearly understood. Let's demarcate clearly the system and surroundings. So what is my system here? My system is the gas. The gas which is present inside the cylinder is my system. That's all. Nothing beyond that is my system. Only and only the gas which is present inside the cylinder is my system. That means whatever is outside that is my surroundings. So the entire atmosphere outside the piston, the entire environment outside the piston and outside the cylinder are a part of my surroundings. What I'm trying to highlight here is that the surroundings are much larger than the system. That means I can say that the surroundings, are an infinite, or the surroundings are infinite as compared to the system. System is only a tiny part of the universe. That is only the cylinder containing the gas. That part is my system. Whatever is lying outside the system is a part of surroundings. Now, because the surrounding is extremely large, so it is considered to be infinitely large, or it can be considered to be much larger as compared to the system. Now, this means that slowly and gradually, any minute change, let's say I'm making a small change in my surroundings or in the atmosphere. Let's say I'm taking some heat from the atmosphere. Now that whatever heat I'm taking from the atmosphere will not create any significant impact on the atmosphere, because the atmosphere is much larger than the system. So the atmosphere around, or the environment around my system, is like a reservoir. It's like a reservoir. Why is it like a reservoir? It's like a reservoir, it's like a heat reservoir, because it is much larger than the system under consideration. And so any change in the reservoir will not create any significant impact or change in the surroundings. That means if I'm taking some heat from the surroundings, nothing much is going to happen. Maybe the temperature will just change by 0.0000000001 degrees Celsius. That is a negligible change. Similarly, if I am releasing heat to the surroundings, let's say something has happened, some reaction has occurred, and heat has been given out because of the reaction. So, will I say that the surroundings have become hotter now? No, I won't say. I'll say again it is an infinite thermal reservoir, as a result of which the temperature of the reservoir or the surroundings is not going to change. That means any heat released to the surroundings or any heat taken from the surroundings is not going to create any significant change in the temperature of the surroundings. Conclusion is this. I repeat, any heat released to the surroundings or any heat taken from the surroundings is not going to create any significant impact on the temperature of the surroundings. So I can still safely assume that despite the fact that heat has been taken or lost, the surroundings are still going to be maintained at a same or a constant temperature as before. Okay. Why? Because the surroundings are like a thermal reservoir, and the reservoir is much larger than the system under consideration, because the system is just a tiny part of your universe, extremely small part that you are studying. Whatever is lying outside it is the surroundings. So compared to the magnitude or the size of the surroundings, the system is just a very small particle, or maybe it is just a very small portion of the universe. So the system is undergoing many changes because of the processes that it is being subjected to, but the surroundings are ultimately having no change in their conditions. So the surroundings are like a thermal reservoir. So the temperature of the surroundings is not going to be changed. it is only a very small amount of change that is expected, and that too is nullified because it is an infinite thermal reservoir. So after some time, again, I can see that the temperature has become same as what it was before. So there is no change, there is no permanent change in the temperature of the surroundings. Now, coming to the process of reversible expansion. Reversible isothermal expansion, to be precise. So I'm talking about a reversible isothermal expansion now. What will happen now? If this gas has to expand reversibly, slowly and gradually I'll start removing the sand particles one by one. So if I remove one sand particle from the surface of the piston, then the piston will rise maybe by a very small amount. So it will rise by a very small distance. It will rise up. Again, if I take out one more sand particle, or if I remove another sand particle from the piston, again the piston will move up by a very small distance. So again, I can say that the gas has expanded by a very small distance or by a very small volume. Again, if I take out or remove another sand particle from the top of the piston, the gas will again undergo a very slight expansion because of the piston moving up by a very small distance. In this way, by removing the tiny sand particles one by one, I can cause expansion of the gas. But this expansion will be termed as a reversible expansion. Why? Because very slowly and gradually the change is taking place. So once it is here, that is initially, let's say it is here, the piston. The position of the piston will indicate the position of your or each particular point on the curve that you draw in a graph. So this position was initial. Slight change, that is, if I just remove one sand particle, then it will come up maybe by this distance. Again, if I remove one more sand particle, it will come up and lie at this point. In this way, slowly and gradually, I'm indicating the positions of the piston like this. So very slowly and gradually, the piston will move up. Now, when the piston is changing its position, that is from one point to another point when it is going upward. Can I say this that already we have learned this, but I'm repeating that let's say now when the piston is here, because the piston has gone up very slightly, so now can I say that the external pressure acting because of the existing sand particles, the external pressure acting because of the existing sand particles is almost same as the pressure of the gas present inside. Why? Because the piston has moved up only by a very slight distance. So because of that, I can say that the pressure of the gas is almost equal to the pressure of the sand particles, right? Similarly, again, when the piston moves up here, that is, it again goes up here. Again, I can say that the pressure acting now because of the existing sand particles is same as the pressure of the gas. So what I'm trying to say is, at each and every point during this reversible expansion, there is equilibrium maintained. At each and every point during a reversible process, equilibrium is maintained. What do I mean by equilibrium in this case? I can say that the external pressure is same as the pressure of the gas inside. This is at every point in a reversible process. At every point in a reversible process. Why so? Because the piston is moving up and immediately coming to rest. The piston is moving up by a slight distance and immediately it is coming to rest. When a piston has come to rest, what does that mean? It means that it has come to rest because the external pressure is exactly balanced by the pressure of the gas present inside. Then only a piston will stop. It won't move further. So when the piston has stopped moving, I can say that equilibrium has been achieved because the external pressure is now exactly equal to the pressure of the gas. Similarly, again when the piston will move up by a slight amount, again after moving it will stop. So in this way, I will have multiple positions of the piston between the initial and the last states of the piston because I'm lifting the sand particle one by one. With each removal, the distance is moved, right? With each removal of a sand particle, the distance traveled by the piston is increasing. That means the piston moves up as and when I remove one particle. When I remove another particle, again the piston moves a little upward. Again I remove another particle, the piston moves a little upward. So in this case, I have multiple positions or possibilities of the positions of piston. Each position, each such position is giving me a point lying on the curve that we plot between pressure and volume. So the graph plotted between pressure and volume for a reversible process is nothing but giving you all possible points lying on the curve, and those points correspond to the positions of the piston. So every time a piston achieves a new position, we get a new point on the curve. So every position of the piston is characterized by a point on the curve that you plot between P and V. So this is because we are able to make the process happen extremely slowly. Because it is happening extremely slowly, it is called a reversible process because at each and every point the piston is stopping. It is stopping. Again, if I remove one sand particle, it is again moving and stopping. Again, if I remove one sand particle, again it will move slightly upward and then stop. Again, if I remove another sand particle, again the piston will move a slight upward and then stop. This will keep happening until and unless I reach the final state or the final state that is B, or is if B is my final state. That is A is my initial and B is my final. I'm calling it B just to make it easier to understand. So if B is my final state and A is my initial state, between the final and initial states, there are numerous or there are infinite such possible positions of the piston. So very slowly and gradually the piston is moving upward because it is reversible expansion. And in this process, it will absorb some heat. It will absorb some heat from the surroundings. Okay. So the heat is exchanged because the wall is conducting. So I'm permitting heat to flow inside. So if the gas is reversibly expanding, I can say that every position of the piston gives me one equilibrium position. So every position of the piston, because the piston is stopping at every point, I can say that every such position of the piston tells me that the pressure existing now due to the remaining sand particles is same as the pressure of the gas. So the pressure of the gas is same as the pressure acting on the piston as a result of the sand particles present on the piston. So this is possible only and only because I'm having infinite positions of the piston between A and B. Between A and B, so many times the piston is stopping, moving and stopping, moving and stopping, moving and stopping, moving and stopping. Why is it moving and stopping? Because I'm changing the number of sand particles. Basically, I'm changing the pressure. So at every point, I have a different pressure acting on the piston, and that pressure is nothing but the same pressure which the gas is achieving. So I can say that every point gives me an equilibrium point. Why is it an equilibrium point? It is an equilibrium point because the pressure of the gas is equal to the pressure acting because of the sand particles. So this is a reversible expansion. Now, it is isothermal. If it is isothermal, that means the temperature is same. That means the temperature of the gas is same. How is it same? It is same because I'm allowing the flow of heat from the surroundings to the system. So from the surroundings to the gas, there is a flow of heat, which is maybe denoted by dq. So
Sir,
this is, yes,
sir, the pressure applied by the sand particles would be equal to the pressure of the gas only when,
the
uh,
piston has stopped.
no, sir, when the system is in vacuum, right?
No. Any case, no. When the
Sir,
system,
but
when the
what,
no. What I'm trying to say is, when the piston has stopped, why has it stopped? It is stopped because the pressure, this pressure is exactly same as this pressure.
sir, but what about atmospheric pressure?
There is no atmospheric pressure now, no? You are putting sand particles ka pressure. So the pressure is exactly same as the pressure of sand particles plus the atmospheric pressure maybe that we are considering. But we are currently focusing on the sand particles because the pressure of sand particles is much larger than the atmospheric pressure. Atmospheric pressure is just 1 atm, right? If you add 1 atm, if you add 1 atm to let's say 11 atm, it is what? 12 atm. So I can approximately say that the external pressure is 11 atm because that 11 atm is coming from the sand particles, right?
Okay, sir.
So the pressure acting is because of the sand particles. Yeah, atmospheric pressure is there, but we can ignore the atmospheric pressure because the pressure exerted by the particles of sand is much larger than the atmospheric pressure. So the total pressure, if you want to find out, then you can say that yes, it is the sum of atmospheric pressure and the pressure of sand particles. But if I just say that what is the major portion of pressure, the major contribution is coming from the sand particles. So the sand particles are exerting pressure on the piston, right? But when I'm removing a sand particle, the pressure is decreasing. So the new pressure is what is now acting. Because I have removed one sand particle, the new pressure will be only because of the existing sand particles. That pressure is what is going to be achieved by the gas, and that is where the piston will stop, right? So as and when I remove the sand particle, I'm adjusting or decreasing the pressure that is being applied on the piston. That means the external pressure is falling at every point. The external pressure is falling at every point. Why is it falling? It's falling because I'm removing the sand particles one by one. So if I remove the sand particle, the pressure will fall. The moment the pressure falls, the piston moves upward and the gas achieves that same pressure which is being applied on the piston because of the existing sand particles. So every position of the piston tells you a different value of pressure. Okay. Every position of piston tells you about a different value of pressure. Why? Because the number of sand particles has decreased. As you are decreasing the number of sand particles slowly and gradually, the pressure is also falling slowly and gradually. And that pressure which is falling is nothing but being achieved by the gas. And that is where the piston stops. Okay. Now, because it is isothermal, the temperature is constant. So the temperature will remain constant, and I'll say that T is the temperature. So T is the temperature. If I say that T is the temperature of the system, also I can say that T is the temperature of the surroundings. Why? As I said, if I'm taking heat from the surroundings or if I'm releasing heat to the surroundings, it doesn't matter to the surroundings because the surroundings are much larger than the system under consideration. So nothing is going to happen even if I add heat to the surroundings or if I remove heat from the surroundings are still going to be maintained at the same temperature. Surroundings में इतना कोई असर होता नहीं है because surroundings is like a thermal reservoir. It is much larger than your system. So that means the system is also at temperature T because it's isothermal and the surroundings are also at a temperature T now. If I want to find out the change in entropy, that's what I'm trying to show now. Now, change in entropy. Delta S, right? Delta S system is equal to dq system. The process is reversible, so by default I can take the same value of dq, that is actual dq. Why? Because the process itself is reversible. Since it is a reversible process, I can directly use the value of dq upon temperature. The temperature is constant because it's an isothermal process. So I can take this temperature outside the integral sign and I can place temperature here. So this is what I can do. Correct? Because it's constant. Any constant is taken outside the integral. Now if I want to carry on this integration, I'll have to apply the first law of thermodynamics, right? dq, now we know that du is equal to dq plus dw. We know this. Also, we know that du for an ideal gas is ncv dt. Ideal gas is being considered in this chapter. If nothing is mentioned, we will focus on ideal gas. dw is nothing but minus pdv. Right? dq plus minus pdv. Because it is a reversible process, I told you that P gas is same as P external at every point, because every point corresponds to a new position of the piston wherein the external pressure due to the existing sand particles is exactly balanced by the pressure of the gas. So pressure of external, that is sand particles, is same as the pressure of the gas at every point of the piston. So I can safely say that P external is same as P gas. So this P is nothing but I can say that it is pressure of the gas. Why? Because it is same as pressure of the sand particles. This P actually refers to the pressure of the sand particles. But because the pressure of sand particles is same as the pressure of the gas, I am taking pressure of sand particles equal to the pressure of the gas inside. This is only possible because it is a reversible process. So at each and every point you have equilibrium maintained. So this P which I'm using is actually the pressure of the sand particles, which is continuously changing. But because the pressure of sand particles is same as pressure of the gas at every point, so I can directly say that pressure of sand particles is P, and that P can be safely assumed to be pressure of the gas. As per ideal gas equation, PV is equal to nRT. So P gas will be equal to nRT upon V. So P gas will be equal to nRT upon V. Correct? Any doubt in this portion? Okay. Now, if I want to carry out this, if I want to find out the value of dq from here, then what will I say? I will say that, therefore, ncv dt is equal to dq plus this pdv is what? Minus nRT by v dv. Okay. Pressure P of the gas is nRT upon P as per ideal gas equation. So I'll get this. On solving this further, I can say ncv dt plus nRT upon v dv is equal to dq. Right? So I've got the value of dq now. Now put that value of dq here, delta S system. Delta S system will be equal to this for reversible isothermal process, right? We are following this for reversible isothermal process. Now, for an ideal gas, of course. So delta S system will be what? 1 upon T, because its isothermal temperature is constant. I can take temperature outside the integral. And this dq is nothing but NCV dt plus nRT by VT. N is a constant, I can take it outside. T is a constant, I can take it outside. So I'll be left with CV dt plus R by V dV. T and T will get cancelled. So this will be N. I can write this like this now. CV dt plus R by V dV. Because the volume is changing if it is expansion or compression. So I can say from V1 to V2. V1 is the initial volume, V2 is the final volume. So the integration will take place between V1 and V2 for this portion because dV is given. So for dV, I have to put the limits of V. What are the limits of V here? V1 and V2 are the limits of V. These are called limits in mathematics. Limits of V. So what are limits of V? V1 and V2. Why so? Because the limits correspond to the initial and final values of a variable. Now, CV dt. Now tell me one thing, what should be the value of CV dt for an isothermal process?
0.
Why?
Temperature is constant.
Exactly. Since temperature is constant in an isothermal process, I can say dt is 0. See, if anything is constant, d of that thing also will become constant, will become 0. So dt is 0 as temperature is constant. dt is 0 because temperature is constant in an isothermal process. So I can clearly remove that term. So it will be 0 plus. R is a constant, it is 8.3148. So I take it out and I'm left with now 1 upon V dV. So this particular derivation that I'm doing is for reversible isothermal process. Now, integral 1 upon V dV from V1 to V2 is called ln V2 upon V1. Right? Integral of 1 by x dx from x1 to x2 is given by mathematically ln x2 by x1. This is the formula. This formula has to be known to you. I'm sure you have done this in physics. Okay. Or in chemistry, if I want to convert ln to log, that is if the base of log has to be 10, I have to multiply this by 2.303. So this formula becomes 2.303 nr log V2 by V1. That means if I write log in chemistry, by default the base is 10. By default, the base is what? 10. So I can say that ln x is equal to 2.303 log x to the base 10. This also has to be known. So I've achieved the value of final delta S system. So this is delta S system for a reversible isothermal process. What about delta S of surroundings? Now see, I told you that the surroundings will also be at the same temperature, right? The surroundings will also be at the same temperature. Why? Because after I take some heat from the surroundings, or after I release some heat to the surroundings, there is no appreciable or significant change in the temperature of the surroundings, because the surroundings are much, 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 much larger than my system. So I can say that the temperature of the surroundings is now T, that is same as the temperature of the system. So again, I will say this one. And now it is dq surrounding. One by T. Okay. Now, can I say one thing? That is, whatever heat has been lost by the surroundings is nothing but the same heat which is gained by the system, because the system has taken the heat from the surroundings only. Or in another way, I can say that if the system is losing heat, then the surroundings are gaining that same heat. So in either case, I can say that the magnitude of heat is the same. That means heat lost by surroundings is equal to heat gained by system. Or I can say that heat lost by system is equal to heat gained by surroundings. If system is absorbing heat from the surroundings, that means the surroundings have lost that heat, right, to the system. So the magnitude is the same. Whatever heat has been lost by the surroundings is nothing but the heat which is gained by the system. Or whatever heat is gained by the surroundings is nothing but the heat which is lost by the system. So I can say that dq surroundings is nothing but equal to minus dq system. This is nothing but minus 1 upon t integral of dq system. So dq surroundings is equal to minus dq system. Now, this entire thing has been already found out by us. This entire thing has been already found out by us here. See, this is the value. So I'll put that value. This entire thing is dq system, right? This entire thing is delta S system, which is 1 by T integral of dq system. This entire value is what? This entire thing is dq system. So I can say that this entire value is known to me. So I'll put equal to minus 2.303 nr log v2 by v1. So this is what this is delta S of surroundings. Can I say if I add up the two things, that is delta S system plus delta S of surroundings in this reversible isothermal process? So can I say it comes out to be 0? Why? This is delta S surroundings and this is delta S system. The values are the same, just the signs are opposite. This is what is delta S system. Correct? So delta S system plus delta S surrounding is equal to 0 for reversible isothermal process. That is the process that we just now did. So delta S system plus delta S surroundings is equal to 0. In fact, remember, for any reversible process, delta S system plus delta surroundings is always equal to 0. So I gave you the proof for a reversible isothermal process only. Similarly, for an adiabatic process also we can do. If it is a reversible adiabatic process, what will happen? Delta S system.
Q will be 0.
Exactly. So delta S is equal to dq upon p. If it is a reversible adiabatic process, I can say that this is 0 by 0 because in a reversible adiabatic process, no heat is gained or lost. In a reversible adiabatic process, no heat is gained or lost. Delta S surroundings. The surroundings have not undergone any change because it has not gained or lost heat because it's adiabatic. Since the process is adiabatic, the system will neither lose heat to the surroundings nor will it gain heat from the surroundings. That means the surroundings are not able to gain or lose heat. So there is no heat exchange at all between system and surroundings. So it is also 0. So if I again add up delta S system plus delta S surroundings, again I can say that this will be 0. Correct? So this is for what? This is for reversible adiabatic process. Right? This is also for a reversible adiabatic process. So again you can see that for a reversible process, total delta S is equal to 0. What is total delta S? Delta S system plus delta S surroundings. Okay. Coming to irreversible adiabatic isothermal process. Irreversible isothermal process. Now the process is irreversible, but I have told you that mathematical definition of dq system is always that dq which will occur when the system is undergoing a reversible process. So even if the actual process is irreversible, the dq system will be taken only and only for a reversible process. So if I want to find out the value of delta S system in this case, again I have to say this. Means what? Means the value of dq for system, the value of dq for system will be that value of dq which would have been the case if the process had been reversible. So for a reversible isothermal process allowing the same final state B, what would be the value of dq? That is called dq reversible. Means what? It is nothing but equal to that same thing which we did earlier because that was also for reversible. So I can say delta S system will be same as this value. Again, I'll put the same derivation, same formula. All these things will be done. So delta S system will be exactly equal to this 2.303 nR log V2 by V1. So even if the process is irreversible, the delta S system is going to be calculated for the reversible process. So this is the value. So this is the value of delta S system. Any doubt? Anybody has? Now delta S surroundings. But I told you in the beginning that for delta S surroundings, the dQ that we use is the actual value of heat. Now it is not going to be assumed as reversible. Now it is actual. What is actual? The actual is irreversible, right? So if the actual is irreversible, then for surroundings also we are going to consider the actual heat, which is in the irreversible process. So the difference is that for delta S system, you assume it to be a reversible process, but for delta S of surroundings, you assume the dQ for a proper process, which is the actual process. So here the actual process is irreversible. So delta S of surroundings will also be taken into consideration by considering the dQ of the irreversible process. Now, can I say that in this, the actual heat gained or lost by the surroundings will be calculated in this manner, that is in this way. Now try to understand this. This is a bit confusing. Look at this. For system undergoing for system undergoing irreversible process. Now I'm talking about system. I'm not talking about surroundings. I'm talking about the system now. For system undergoing an irreversible process, I can say that W is equal to minus P external into V2 minus V1. This we have done. Work done in an irreversible process is given by this formula. Okay. So W is equal to minus P external into V2 minus V1. Also, I can say that if the process is isothermal, if the process is isothermal, because currently I'm talking about an isothermal irreversible process, then U is equal to 0. I mean delta U. Delta U is equal to 0 since temperature is constant. Why? Because we know delta U is equal to NCV delta T for an ideal gas. Since there is no change in temperature, I can say safely that delta U is 0 because delta T is 0. So applying the first law now. Applying the first law of thermodynamics. Applying the first law, we can say delta U is equal to Q plus W. 0 is equal to Q plus W. So Q is equal to minus W. And what is W? W is for an irreversible process. W is this minus P external into V2 minus V1. So I can say W is minus P external into this. So Q will be equal to P external into V2 minus V1. But this Q is the actual heat exchanged by the system because I have applied this for the system, right? This is work done when I'm doing for the system, right? So the system, for the system, I've applied the first law and I've found out the value of Q. This is all for the system. But can I say that if this is the Q exchanged by the system, the magnitude of Q exchanged by the surrounding will also be the same, because whatever heat is gained by the surroundings is nothing but the heat lost by the system, and whatever heat is lost by the surroundings is nothing but the heat gained by the system. So I can say that, therefore, Q surroundings or since we can say that since Q surroundings is equal to minus Q system, therefore Q surroundings is equal to minus, this is Q for system, this thing, this Q for system. So Q for surroundings will be equal to minus of this. This is going to be the Q for surroundings. And so delta S of surroundings will be equal to T is constant because it's isothermal. So this is going to be the delta S of surroundings when the process is undergoing an irreversible isothermal process. So when the system is undergoing an irreversible isothermal process, that time we can say that this is the delta S of surroundings, and delta S system is same as what it was for a reversible process. So this is delta S for a system. So delta S for a system in an irreversible isothermal process is this, which is exactly same as delta S of system in a reversible isothermal process. So I can say that in both reversible as well as irreversible isothermal processes, the delta S system is the same. I repeat, in both reversible as well as irreversible isothermal processes, the delta S system is the same. Why? Because in both cases, we consider dq reversible. Irrespective of whether the actual process is irreversible or not, we are going to consider the dq which is expected in a reversible process. That is the definition of delta S of system. So using that part or using that mathematical definition, we can say that in both reversible as well as irreversible isothermal processes, the delta S system will be the same. But the delta S surroundings are not the same. Why? Because while calculating dq of surroundings or the heat exchanged by the surroundings, we take the actual process and not the imaginary process. So if it is a reversible isothermal process, then the delta S surroundings is different. If the process is an irreversible isothermal process, then the value of dq, that is the heat exchanged by the surroundings, is different, and that is why the delta S surroundings are different in reversible and irreversible isothermal processes. Because whenever you are calculating the value of delta S of surroundings, you take the actual value of Q. You do not take the Q reversible only. You take the actual value of Q. So if the process is actually irreversible, like we have taken here, then the Q will also be taken for the actually irreversible process. So the Q for the surroundings will be the actual heat which is gained or lost by the surroundings in the irreversible process, because the actual process is irreversible. So here for calculating Q of surroundings, we do not assume a reversible process. We in fact take the actual process which is occurring. But when we are calculating Q of system, that time we always assume the process to be a reversible process and then calculate the Q of system. This is the rule to be kept in mind. Okay. So these are the derivations which I did, just for you to understand. These all formulae are given to you in the form of a list here above. Yeah. So here you have the formulae which we derived, starting with this. So we derived this just now. Delta S system and delta S surroundings for reversible isothermal process, where I told you that delta S system plus delta S surroundings is 0 for a reversible isothermal process. For a reversible adiabatic process also we derived, I told you there is no heat gained or lost. So delta S system is also 0, delta S surroundings is also 0, and 0 plus 0 is also 0. So delta S system plus delta S surroundings is also 0 for a reversible adiabatic process. For an irreversible isothermal process, we derived just now, that is the last derivation which we did. That is delta S system is this, and delta S surroundings is minus P external into V2 minus V1 upon T surroundings. So in the exam, they directly ask you questions based on calculations of delta S of system and delta S of surroundings. For an irreversible adiabatic process, just remember this. We are not going to do the derivation or the proof now. I'll do it someday later. But as of now, just learn this, that for an irreversible adiabatic process, delta S system is positive, that is greater than 0, and delta S surroundings is equal to 0. This is for an irreversible adiabatic process. And for a general expression of an ideal gas, this also we did today, the derivation, that is this one. Not isothermal, in general. In general, this is what you get. Why in general we get this? Because remember when we were doing the derivation for delta S of reversible isothermal process, that time I told you that this dt term becomes 0. This dt term becomes 0. Why it becomes 0? Because in an isothermal process the temperature is constant. This dt will become 0 and this entire term will vanish if the process is isothermal. But in general, if they ask you what is the expression for delta S of an ideal gas, if they don't mention the word isothermal or adiabatic or anything, if they don't mention anything, then dt will not be 0, because then temperature is changing, pressure is changing, volume is changing. In general, we will say everything is changing. It is not isothermal, it is not isochoric, it is in general. So in general, dt will not be 0 because temperature is not constant, if I say. So dt term will remain. So that dt will be 0 only if the process is isothermal. So if the process is not isothermal, dt will not be 0, and I'll have to integrate this from T1 to T2, that is the final temperature is T2 and the initial temperature is T1. and this will be the final expression. Okay. So this is the proof for delta S of gas, ideal gas, undergoing any kind of process. So we'll continue with the other formulae and other kinds of delta S related topics in the next lecture. Thank you.